Okay, so final question of the ionic compounds section. This is question 3. This time we're looking at a potassium bromide structure as opposed to sodium chloride. And the first question is given us a slightly better representation and then more of the repetitive nature of an ionic solid, and it's asking us to write a symbol to show whether or not it's potassium or a bromide ion. Now, there's no differentiation between essentially the white ones and the greyed out ones in this situation, but as long as we correctly identify one of them, so K plus as, for example, the white ones, and as long as we don't then break that repetition, then we're okay for this type of diagram. So that's where the potassium ions will go, and then the bromide ions will go into the grayed out circles. And as long as we get that repetition, then we're okay for this type of thing, because we can see that the positive charges are being attracted to a negative charge, which has been attracted to a positive charge, etc., etc. And as long as we get that alternation in this type of situation, then we're okay to answer the question. One important thing is to not miss off the charges, because obviously you need to represent the charges as they go. Now, when we have this type of diagram, moving on to question 3.2, there are advantages and disadvantages. Like a previous question where we had limitations of a dot cross diagram, we've got limitations and advantages to this type of diagram as well. And the big advantage of this type of situation is we can see the three-dimensional structure of what's actually going on. We can see how the potassium ions and how the bromide ions are arranged. It shows the extension of the structure and gives some idea that this structure is going to carry on theoretically indefinitely. And you can see that type of situation. The disadvantages, again, is how we've drawn the diagram, but there's no reference to size. We're not aware from this diagram whether or not a potassium ion is bigger than a bromide ion or vice versa, and it's quite likely that they're not very similar sizes in this situation, so we're not aware of those. And also, like any type of diagram when we draw this is a solid, and there shouldn't be any gaps between these particles. These particles should be touching because you can't compress a solid, etc., etc. So there shouldn't be any gaps in there, so we don't get the kind of correct solid arrangement as we would originally see. So we don't want to see gaps in a diagram of this nature. Now, the empirical formula can be worked out, again, in the same way to how it can be worked out from a dot cross diagram. And we literally look at the ratio of the two substances, and we can see that generally there's one potassium for every bromide, but also we know that it's a K plus with a singular positive charge and a bromide minus with a singular negative charge. And in an ionic solid overall, the charge would be neutral, so we need one of each to balance out the charge. So we know we've got K1, Br1. So if we just go into the final question, then we've got some properties of an ionic solid, of an ionic structure, potassium bromide, and we're looking at three things: boiling point, electrical conductivity of solid, and then of a solution. Now, the boiling point in the situation here, that's a high boiling point. And why is that so? So for the boiling point, ionic substances, as we've started to look at in a previous question, they are giant ionic lattice structures, giant ionic structures. And giant ionic structures have strong bonds, and they need a lot of energy to break all those bonds. So they've got strong bonds, and it needs a lot of energy. That's why it has high boiling points. So it needs a lot of energy to do that. And looking then at the electrical conductivity, we've got a difference in conductivity. For the solid, it's low. For the solution, it's high. Now, in both situations, conductivity requires the movement of ions. So in a solid, the ions cannot move, whereas in a solution, the ions can move, and subsequently they can then carry the charge through the structure, etc., etc., and allow that to conduct.